As Mark had alluded to prior to lunch, so this afternoon we've got a very exciting schedule. So we'll start off with 2 talks on digital television, and then Tom will come on and tell us about how he does communications for the Marine Corps Marathon, and then pulling anchor here will be Bob Bernenga. Mark, you ready?
Yeah, we're going to do this with Skype for audio and Adobe Connect Now for video. Ken, W6HHC, and Robbie are both in Orange, the county of Orange and the city of Orange in California. They've been doing some very interesting work, and so I'm going to go to the back of the room and have my headset on, and the presentation is going to come up on the screen. If you could minimize your internet use, done a lot of big file downloads because we don't have a lot of fast internet in this hotel. I don't think it's going to be a problem, but just wanted to make certain. And then after that, Art will come up. We're going to take some Q&A when Robbie and Ken are done. Then Art will be next and talk more about digital television. This is a really interesting topic, and I'm really excited that they could do it. So I'm going to go in the back now. We're going to get everything thrown up.
Good afternoon. Welcome to the TAPR presentation called Planning a Digital Amateur Television Station on DVB-S. My name is Ken Konecki, W6 Hotel Canada, and I'll introduce my partner, Robbie. Robbie, why don't you introduce yourself?
Hi, I'm Robbie Robinson, KB60JZ, and I'm in the city of Orange, California.
Well, thank you very much. And during this presentation, we're going to cover a lot of ground, so I'll probably go very fast, but hopefully have time for questions and answers at the end. But we're going to start off by talking about different digital television standards that exist in the world that hams can choose from. We'll then go through a planning session to see if we can figure out which digital television standard is best for ham radios or through our eyes here in California. And then once we choose a standard, we're going to end up choosing DVB-S over the American-based standard called ATSC. We'll then go and look at one of the things that digital amateur television offers is a smaller bandwidth. What I'd like to kind of introduce you to is why did we start this project? And both Robbie and I are members of a couple of organizations, and we've been involved with some really interesting conversations that all went like this. We hams should change from analog amateur TV over to digital amateur TV to keep up with technology. Sounds simple, sounded like a good goal, and the problem was we spun our wheels for a couple of years, and nothing happened. And the reason was it was complex enough, and we just couldn't get our arms around it. And so finally started putting some papers together to help understand what was involved. I think the first thing you have to do is ask the question, why go digital amateur television? And the most important reason, I think, is the picture quality. It can be literally perfect most of the time. Digital communications allow error correction techniques, which will help you with noise and multipath. Digital communications allow you to use advanced modulations, which give you things like compression and smaller bandwidth. And for hams, eventually digital TV components will become available in common upon eBay. And vice versa, analog TV components for hams will start to disappear as that becomes an obsolete technology. Well, let's talk about the 4 main standards that hams have been looking at for digital amateur television. DVB-C is a cable version of DVB. DVB stands for Digital Video Broadcasting. It's used mainly in Europe, in Asia, and Pacific. It has 3 varieties. It has DVB-S, which is a satellite set of protocols and a standard. It has DVB-T, which is a terrestrial type of standard for mountaintops to your home dish or antenna. And finally, here in the United States and in Canada, you have ATSC, which is used for terrestrial type of communications. So let's walk through each one of these. DVB-C, the cable version. Interesting thing about a cable environment, it's a very low loss environment, not like hams at all. The cable environment is almost noise free. It's free of multipath type of issues. And this allows the cable people to use higher order modulation schemes, very sophisticated ones, always up to 256 QAM, and able to do it successfully because the signals are loud, they're strong signals. It really does not represent a good choice for hams to consider for digital ATV. So let's take a look at DVB-S, the satellite type of standard. It uses a very simple quad phase shift key modulation scheme. It is very good for satellite environment, which was a very high loss type of environment, but it was not designed to deal with multi-path problems because they don't exist in the satellite. But it does layers of forward error correction, known as FEC, that gave very robust protection no matter what type of error is occurring. What I like about DVB-S is that you can get a bandwidth as small as 2 megahertz for video and audio. And the other advantage is it was chosen by a lot of European groups, hams, and the only active digital television station in the United States right now is using DVB-S. The next standard is DVB-T, terrestrial, and it's very robust and designed to really overcome the destructive effects of multipath reflections. It uses a 16 QAM modulation scheme at a very low bit rate per carrier, and then it puts 1,700 of those carriers very closely spaced using something called coded orthogonal frequency division multiplexer, which could be a talk by itself. And the fourth one is ATSC, which stands for the American Television Standards Committee. It's used for terrestrial. The modulation scheme is a 8-level amplitude scheme. Like DVB-S, ATSC uses MPEG-2 for video compression, but it deviates from DVB-S in that it uses a different algorithm for audio compression. It uses a algorithm called AC3, which is owned by Dolby. Also uses multiple layers of forward error correction and very robust protection. And a real big attraction of ATSC is that set-top boxes in the United States are very cheap. I mean, they were selling for $40 new. I'm sure that there's a lot of those things that are going to be available for years to come. Well, we talked about the advantages of digital amateur television. Are there any drawbacks? And in my mind, I see 2 areas that are difficult for digital ATV. One is weak signal reception. And what you see is that as the signal gets weaker and weaker, you still have a perfect picture. It's perfect, it's perfect, it's perfect. You start to get a little bit of pixelation, and then poof, it's gone. So it's almost an all or nothing type of a scenario. And as one of the gentlemen in Central Ohio pointed out, that he doesn't expect to see a lot of DXing occurring with digital amateur television just because you can't see the signal in the noise unless you have a spectrum analyzer. And that's not a typical ham DXing tool. The other drawback I see is the high cost of digital amateur television equipment. When you have analog ATV, you had a lot of cheap surplus equipment you could use, especially for digital amateur television transmitters. There's nothing that's surplus commercial yet. Okay, let's take a look at a typical block diagram of a DAT. You have the camera, an analog camera source over here. It goes into a MPEG compressor. The compressed digital comes out and goes into what's typically called a broadband processor where a lot of digital processing is done to do the forward error correction calculations and to create the I values and the Q values. And then this digital stream is sent over to the RF section of the unit where the I and the Q values are modulated in QPSK, and then you're up converted to whatever your RF frequency is. You put it into a very linear amplifier. It has to have a lot of headroom, be very linear. You've got a lot of peak to average power to consider there. And 3-to-1 or 4-to-1 is very typical. And if you took that diagram, here's an early prototype out of Germany. This was shown, I think, in 2002 over at the largest Hamfest in Germany, which is a lot equivalent to our Dayton. Here's the MPEG-2 in the lower right-hand corner. This is the baseband processor going on. Here's the uploader to 1.2 gigahertz, and here's the big power amplifier in the upper right-hand corner. So it was made to look very easy. A lot of hard work was done to make that happen. And then here's the comparison of what you get. So here's where digital ATV is today. This is a great side-by-side comparison. Same antennas, both sending and receiving, weak signals. And you can see this is the analog, and here's the equivalent digital ATV on the digital ATV machine. They were just using switches to switch back and forth between the two. Great comparison picture. So we said, okay, now we've want to do this. What band do we plan? And in Southern California, that's not an easy topic. You have to study the band conditions very carefully. 440 megahertz is a very crowded band. I don't think we can get digital ATV on that band easily. But it had the advantage of RF amplifiers being cheap. 920 is a very tight fit for a DATV, and it has what's called ISM Part 15 devices. Lots of noise there. ISM is instrumentation, scientific, and medical devices. 1.2 looks very good. Certainly, we've got room for a simplex digital ATV signal. Probably not room for a pair, but it's a clear band. It's not shared with other devices. You can look at 2.4 gig, lots of room. This region around 2.4 is shared with other commercial services. So if you're in a repeater site that has lots of commercial things, there's some possibility of interference or problems. Also, there are some Part 15 devices. 3.4 looks also very good. Has room probably for a repeater pair. And it's only shared with the U.S. Air Force, so it's a pretty clear channel. 5.8 is kind of narrow and probably doesn't have room for a repeater pair. It's also shared with commercial services, Part 15 devices. 10 gigahertz is a nice place, but amplifiers are really getting expensive now. It's a clear band, so it's always the last resort. So what band did we plan? Well, our planning right now is that we're going to have our initial home transmitters and some portable field transmitters we're planning. We're going to put those out on 1.2. Our plans are downstream. We'll add a digital amateur television repeater, and we'll probably either be on 2.4 gigahertz or 3.4. I think right now we're favoring 3.4. Okay, so the next question is, well, what modulation scheme are we going to use? We're going to use the ATSC scheme, or are we going to use the DVB-S scheme? So let's kind of look at each one of these two carefully and start with DVB-S. Uses a nice simple modulation scheme, quad PSK. Both the video and the audio are compressed using the same algorithm, MPEG-2, so that simplifies things a little bit. And a transmitter looks much like what we saw before. You have the analog camera coming in. You got the MPEG compressor. There's a company in Germany called SR Systems that has now put all of the transmitter and the data processing on one board, basically call it an exciter. And so it does the forward error correction processing, it does the IQ modulation, it does the QSPK, and out comes 1 milliwatt of 1.2 gigahertz signal. And you can do this for 440, you can do it for 900, whatever band you want. Put it into a kind of a small amplifier, you build up the 1 milliwatt to maybe 20 milliwatts or something like that, then put it into a very linear amplifier, and we're hoping we'll get 10 watts. So this is a DVB-S transmitter. The cost, basically, it will probably cost somewhere between $1,000 and $1,200, somewhere in that region. The reason there's two prices here is European hams have to pay for VAT tax over there. These prices do not include VAT tax if you buy from Germany. What's missing here is shipping cost and some wire transfer cost and some conversion to euro cost. But, you know, this gives you an idea of what the costs are currently. Okay, so let's take a look at ATSC transmitter, which modulation scheme. They use an 8-level amplitude modulation. They have an MPEG-2 compression for the video, but then they use a different algorithm for the audio. They use AC3, which is a Dolby product. And the complication starts to be that SR Systems has an ATSC board, but it doesn't use the AC3 algorithm. And that's because of some license cost issues. Here's a picture of the way that SR Systems does it. You still have the analog coming into the MPEG, but you can see that in the SR Systems, they have the audio come in the MPEG also. Out comes a 1 milliwatt ATSC signal using the VSB modulation. And basically, you just use the same equipment to power it up to whatever your level is. So looks almost the same as what we had before, just a different modulator scheme. Let's continue with ATSC. As I said before, there's an issue that the ATSC board does not use AC3 algorithm. They use the MPEG for audio. To my knowledge, no U.S. ham has been able to succeed in using the SR system board or any of the other boards coming out of Europe for ATSC on a set-top box. The set-top box is expecting AC3, and it's not seeing it, so you don't get any audio. There's a ham in Central California, I think it's Santa Clara, Nick, N6QQQ. He hasn't succeeded here, but what he has done is he's been able to use a cable-ready digital television unit. So he puts the STC signal into it, and the cable-ready digital TV uses MPEG-2 audio on the cable. And so it actually sees it, it recognizes the MPEG-2 audio, and out comes the audio. So he's overcome that issue with the Dolby, the lack of Dolby. The other approach that Nick has done is he's used what's called tuners that you can put into your computer. So you can buy STSC television tuners for either PCI or USB and then use it with a computer. The computer can recognize the MPEG audio coming over and do the decoding of the MPEG audio on the computer itself. And so there's ways to work around this lack of Dolby issue. Okay, we've talked about the transmitters a little bit. Let's take a look at how do you receive an ATSC signal. Well, there's about 4 ways to do it. If you have the SR system signal coming in with the MPEG-2 audio, you'd go into a down converter. You'd send that to an ATSC set-top box, and your video would come very nicely over to an analog television. The only problem would be you don't have any audio. If you put a cable-ready digital television unit there, you can take the signal through a down converter. The RF goes straight over to the television, and the television sees the MPEG to audio, and the video and the audio coming nicely. You can also do things on computers. As I said before, you can get a PCI-based TV tuner for your computer, and basically it sends over the signals to the computer. The computer has to work on converting the MPEG to audio into real audio. Likewise, you could have a USB-based TV tuner, sometimes called a stick tuner for ATSC. Plug that into your USB port, and essentially the audio and the video come over, and the audio is decoded from MPEG-2 by your computer. Okay, let's look at the DVB-S receivers. So again, if you had a SR systems signal coming in, you would have a set-top box for your DVB-S. You can send that to an analog computer, or I'm sorry, an analog TV, and both the signal, the video signal and the audio signal can come over just perfectly. Likewise, you could have a DVB-S box going to a digital TV. That works fine. You could have a PCI TV tuner connected to computers, and basically PCI, everything comes over nicely. In this case, the tuner is doing all the decoding of audio and video for you. The PC is not doing any of the decoding. Here's a case where you have the set-top box and you have a USB port, and you go to a notebook computer. Or the one that I use is over here. I have a set-top box. I'm coming out on S-Video and going to a S-Video to USB converter, and then I'm plugging that into my computer, my notebook, and I get the audio and I get the video. Okay, so here's the situation. We got to choose what we're going to do for our transmitter station. So we chose to use DVB-S, and there were two main reasons we used to choose that. One, ATS would mean we'd be always doing trial error. This set of equipment might work, and this set of equipment might not work, all because of the fact that the current amateur boards are sending out MPEG audio, which is a quirk. The other thing that helps sway us is there's a DVB-S benefits from the fact that there's a lot of experience by European hams and a lot of knowledge over there by European hams, and a lot of articles published by these European hams. I mean, the internet's a great service, and Google's a great service. I mean, you can learn things quickly, and the hams have really been a benefit to ham radio by doing that. Robbie's going to probably choose alternative 5, which is a set-top box to a analog TV. As I said earlier, I'm going to do 9, which is a notebook computer. Okay, well, one of the advantages of using digital amateur television is to get bandwidth, a nice narrow bandwidth. And if you're using QPSK, there's 3 things that control the bandwidth. One is the video stream coming out of your MPEG encoder, the forward error inflation rate, which we'll get into in a little bit, and then that results in a symbol rate that you need to support all of this, and then that determines what the RF bandwidth can be. And just to give you a little visualization of the various data rates going on, right here coming out of the camera is equivalent to about 168 megabits per second for an NTSC signal before it's compressed. If you go into an MPEG-2 compressor, basically you'll get it down to about 2.4 megabits per second data rate. So that's quite a bit of compression that goes on there. If you have your forward error correction set for this, you're going to basically need to support, probably set it up for about 2.25 megasymbols per second. We'll get into that in a little while. So 2.25 megasymbols per second will give you an RF bandwidth that's right around 3 megahertz. Okay, here's a table of data rates coming out of MPEG. Again, the camera is 168 megabits. It's uncompressed, but then compressed, you can see it gets down to somewhere between 1 and 3 under differing conditions. And just for comparison, a high-definition TV camera puts out around 1.5 gigabits per second uncompressed, and they can get that down to about 20 megabits per second using MPEG-2 compression. Okay, one part of digital television that most hams aren't familiar with is called symbol bit packing. Different modulation schemes have different degrees of sophistication in bit packing. A lot of people are familiar with binary PSK, PSK31. Basically, for every state transition of that modulation scheme, you get 1 bit of data out. Quad PSK basically has 4 states, and for every transition of state, you get 2 bits of data out. It's kind of like 2 to the 2. 8-level VSB basically is 2 to the 3rd, so it gets 3 data bits out for every one of the 8 state transitions that can be happening. 16 QAM can get 4 for the 16 states, so every transition from a state to a different state gives you 4 bits of data. And 256 is 2 to the 8th, so basically you can get 8 bits of data. This is called bit packing. So when you see a symbol, what you have to ask is how many bits of data is that symbol carrying? And your symbol rate times your packing gives you what your data rate is. And here's the formula that you can use to calculate what the symbol rate is that you need. Basically, NDBR is the net data bit rate, and that's the bit rate coming out of your MPEG-2 encoder. But that's what you need. That's the net data rate you need to succeed. M2 is the modulation factor, so for QPSK, we said it's 2. Now you get into the 2 different forward error correction. You can set the Viterbi algorithm to different settings. You can set it to 1/2, 3/4. What that means is 1/2 means for every data bit going in, 2 data bits come out. That's a large amount of redundancy, so it inflates your data rate. So your gross data rate becomes a lot higher than what the net data rate is you need for the video stream. 3/4 is a little bit better. For every 3 data bits going in, you get 4 data bits coming out. The Reed-Solomon algorithm is a fixed algorithm, and so for every 188 bits going in, you get a small amount of inflation up to 204. So if you plug some numbers in, I said, well, what if we're have the MPEG-2 coming out at 2 megabits per second, and we set a FEC at 1/2, which is actually 1/2 mathematically. Then you put all these numbers into the formula. You grind it out, and you end up with 2.17 megasymbols per second is what you need to configure your transmitter for. And what's the bandwidth? Well, the formula is pretty simple. 1.33 times the symbol rate will give you essentially the RF bandwidth. In the case above, we ended up with a bandwidth of 2.9 megahertz RF bandwidth. I put together a table. It's a pretty complicated table. The numbers inside the table are the net data bit rate you need. And over here, on the left-hand side, you can see a number of different FEC settings you can choose from. And basically, you can set for a particular symbol rate. So if you set it at 2.25 megasymbols per second, you can see that if I want 2.4 megabits of net data rate, the red ones won't give me that much data. But any of the blue settings or the white settings will give me that. So in this case, a FEC of 2.3 will give me 2.76 megabits per second, which is enough to support my 2.4 megabit coming out of the MPEG-2 encoder, and I end up with 3 megahertz. A lot of data packed into the table. And for different data rates coming out of the MPEG encoder, you just use different colors. Okay, let me wind this up a little bit. So we've tried to explain an awful lot of digital amateur television concepts to hams and to you, the audience. Our goal has been to explain things in a way to help make the transition from analog amateur television to digital amateur television a little bit more straightforward, not as confusing as we found it when we started to research this from 1,000 different websites. Our personal plans are to order a set of boards for the DVB-S from SR Systems. Turns out we've already done that. We have the boards. We've started to do the testing at home and taking some measurements. And our next step is going to start doing some field tests with that. We plan to send some signals for quality comparisons to a local EOC at a police station that we're involved with. And what we really want to do is kind of spread the information, spread the word on digital amateur television, hopefully persuade and coax people to try digital amateur television. Well, that really is a conclusion. In your proceedings paper, and also if you have a copy of the slide presentation, here's a bunch of links we really found useful. I guess right now I'd like to open it up for questions. I think we have a few minutes that we can use for talking to any questions that might have come up during our slide presentation. So, Mark, I wonder if I can get you to moderate any questions.
You seem to have ignored the multipath problem that DVB-S is subject to, and terrestrially we'll have that in spades. That's the first of several questions I have. Do you have any plans to check that out?
Yeah, we're going to do a lot of live field testing to just see what occurs. We hear a lot of good things coming out of Europe. So even though DVB-S wasn't designed for multipath, it seems to work very well. Robert, do you have anything to add to that?
We have a ham up in Idaho that has been doing some testing in helicopters, and he's been really surprised with the robustness of the S1 version there. So it looks like it has a good possibility.
Next question.
Okay. The second question is, well, it's first a statement. I've been able to compress high-definition MPEG-2 down to 10 megabits with very good results. So your statement of 12 to 20, 12 is a little high, but 20 is definitely very high. And then next question, most of the commercial providers are planning to, including satellite, are planning to convert from MPEG-2 compression to H.264 compression carried in a MPEG-2 transport stream. I know there aren't any cheap boards available now, but they will be available shortly. Any comment on that?
Yeah, we haven't gotten to that stage. Are you talking about high definition, or are you talking about the normal, let's say, PAL or NTSC?
Well, for example, the U.S. military in December will drop MPEG-2 totally for H.264 worldwide.
Okay. Right now, there's a lot of equipment available, so I think we'll plan on using it. But once we get our feet wet, of course, we can try other things. And the problem is you've got to have enough people buying equipment to be a motivation for hams to design and sell this equipment. So there's a lot of A lot of hard work went into designing these boards. These are about the 4th generation boards that we're using today.
This is just a suggestion to something to look at for hardware. There's a set of software radio devices called the USRP, and there's been some work done on developing DVB, both transmit and receive using those. It can basically handle about a 6 megahertz RF bandwidth using USB to send the data stream from a PC that does the processing. And that just suggesting that could be something to look at as a hardware choice that might allow you to experiment with either the ATSC or the DVB system.
Well, I'm not sure I can comment on that. I know that a friend of ours who lives up in Idaho has been playing with both of them. Right now, I think we're going to go ahead and try to push forward with DVBS. We've looked as carefully as we could. We've tried to make a conscious decision, and I think we'll just go with the DVBS. We have a lot of playing to do with it. I mean, we haven't tried how far we can compress it down. The nice thing about a lot of amateur television pictures is there's not too much motion on it. And MPEG-2, for example, the compression is very good when you don't have a lot of motion from frame to frame. And I think that's going to be a typical amateur television type application. You know, even if we're watching a burning field here in California for a police department or emergency operations center, there's not a lot of motion in there. If you're in a ham talking, even if you're showing somebody your equipment, there's not a lot of motion in that picture. So you're going to get great MPEG-2 compression going on. If you had a basketball game going on or a high-speed soccer game going on, you could have an awful lot of motion from frame to frame to frame, and therefore you wouldn't get as good a compression rate coming out. So, but we have a lot of work to do. We're just getting started. But again, the presentation was designed to just tell people a lot of the information they need to understand that's involved.
Okay, that's about all the time we have for questions. Thank you very much.
Thank you.